this episode, we build a plain language glossary of essential security engineering terms in a way that helps you recall meaning quickly, not just recognize vocabulary. New learners often feel like cybersecurity is a language class where every sentence contains unfamiliar words, and that feeling can make progress seem slower than it really is. A glossary becomes useful when it does more than define words, because a definition you cannot apply is like a map you cannot read when you need it. The exam will not simply ask you what a term means. It will ask you to use the idea behind the term to choose the best decision, the best control placement, or the best justification. So the goal here is to attach each essential term to 3 things you can remember easily: what it means in everyday language, why it matters in system design or assessment, and what mistake people often make when they misunderstand it. When you can recall those 3 pieces quickly, you can keep your momentum during tough questions and avoid getting pulled off track by confusing wording. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A natural starting point is the word system, because security engineering is not about individual devices in isolation. It is about how parts work together to accomplish a purpose. A system is a collection of components, people, processes, and data that work together to achieve an outcome, and the outcome is what gives the system its meaning. This matters because security decisions should protect the outcome, not just the equipment, and protecting the outcome requires understanding dependencies. A common beginner mistake is to think security is something you bolt onto a single component, like adding a lock to a door, when the system might have many other entrances and pathways. When you see a question about system security, you should expect that the right answer considers interactions, interfaces, and failure modes, not only the strongest control on one part. This system mindset is the foundation for almost every other term, because it keeps you thinking in terms of boundaries, flows, and effects across the whole environment. Another essential pair of terms is asset and threat, because these describe what you are trying to protect and what could harm it. An asset is anything that has value to the organization or mission, such as data, a service, a capability, or even public trust, and it is not limited to hardware. A threat is something that could cause harm to an asset, including a person, a group, a natural event, or a failure in technology or process. These terms matter because security engineering is about making risk-informed choices, and you cannot make those choices without knowing what you value and what could realistically harm it. A common misconception is to treat threats as only hackers, when threats also include insider mistakes, outages, supply chain problems, and design weaknesses that create accidental exposures. When exam scenarios describe unusual conditions like natural disruption or operational error, they are often reminding you that threat sources are diverse. If you remember that threats include both intentional and unintentional sources, you will be less likely to choose a narrow answer that ignores a major risk path. Closely connected are vulnerability and exposure, which sound similar but point to different aspects of a problem. A vulnerability is a weakness that could be exploited or triggered to cause harm, like a design flaw, a missing control, or an error that allows unauthorized actions. Exposure is the degree to which a weakness is reachable or likely to be impacted, such as whether an interface is public, whether credentials are widely shared, or whether a component is connected to untrusted networks. This distinction matters because you can sometimes reduce risk by reducing exposure even if you cannot immediately fix a vulnerability, and engineering decisions often involve such constraints. Beginners often assume that fixing vulnerabilities is the only meaningful response, but in real systems you may need to isolate, segment, monitor, or compensate while a permanent fix is planned. On an exam, a question might present a known weakness and ask for the best next step under limitations, and the correct answer may focus on reducing exposure or adding compensating controls. Understanding the difference helps you avoid thinking in all-or-nothing terms. Risk is another essential term that is often treated as vague, but it becomes clear when you think of it as the combination of potential harm and the likelihood of that harm happening. Risk matters because it is the main language that connects technical decisions to mission and leadership decisions, and security engineering is partly about making that connection responsibly. A helpful way to think about risk is that it is not just about bad things existing. It is about whether those bad things could happen in your context and how damaging they would be if they did. A common misconception is to equate risk with fear, which leads to over-engineering and solutions that slow delivery without reducing meaningful harm. In good security engineering, you aim for justified protection, meaning controls are chosen because they reduce real risk in a measurable or defensible way. Exam questions frequently test whether you can prioritize based on risk rather than picking the most dramatic control. Requirement is a term that seems simple until you see how often projects fail because requirements are unclear or incomplete. A requirement is a statement of what the system must do or must not do to meet an objective, including security objectives like access control, confidentiality, integrity, availability, and accountability. Requirements matter because they guide design choices, and they also become the basis for verification and assurance evidence later. Beginners often confuse requirements with solutions, like saying the requirement is to use a specific technology, when a requirement should describe the needed capability, not the brand of the tool. A requirement should be testable or at least verifiable in some reasonable way, because if it cannot be checked, it cannot be assured. On the exam, when you see scenarios with unclear goals, changing expectations, or inconsistent controls, the best move is often to clarify requirements and trace them through design and verification. Remembering that requirements are about what must be true helps you choose answers that strengthen engineering discipline. Architecture is another core term, and it is not just about diagrams or network layouts. Architecture is the high-level structure of a system, including components, interfaces, data flows, and trust boundaries, and it shapes what kinds of controls are feasible and where they can be effective. Architecture matters because many security failures are predictable when you understand structure, like placing sensitive processing in an untrusted zone or creating a single point of failure. A common misconception is that architecture is only a technical artifact created by engineers, when in reality architecture reflects decisions about risk, priorities, and constraints that often involve governance. When a question describes a system with many integrations, external partners, or mixed trust levels, it is often inviting you to think architecturally, meaning you consider how structure affects attack paths and assurance. Security engineering uses architecture as the place where you turn requirements into a real, defensible design. If you can recall architecture as structure plus boundaries plus flows, you will read scenarios with clearer eyes. Trust and trust boundary are essential terms for ISSEP-style thinking because they appear in many forms across different domains. Trust is the assumption that an entity will behave as expected, whether that entity is a user, a component, a network segment, or a supplier. A trust boundary is a line where that assumption changes, meaning something crosses from a more trusted context into a less trusted one, or vice versa. These concepts matter because controls are often most effective at boundaries, where you can validate inputs, authenticate identities, enforce authorization, and monitor behavior. A beginner mistake is to treat trust as a feeling rather than as an engineering decision, but in security engineering, trust should be minimized and justified. Exam questions often test whether you can identify where trust changes and choose controls that reduce unnecessary trust. If you learn to ask where the boundary is and what crosses it, you will be able to reason about many scenarios even when technical details are unfamiliar. Control is another term that needs plain language clarity because it appears constantly and can be misunderstood as only a technical mechanism. A control is a measure that reduces risk by preventing, detecting, or correcting undesirable events, and controls can be technical, administrative, or physical. This matters because security engineering is about choosing the right mix and placing them where they are effective, not about collecting controls like a checklist. A common misconception is that more controls always means better security, but poorly chosen controls can create complexity and reduce reliability, which can actually increase risk. Another misconception is that a control is always preventive, when detection and response controls are also essential, because not every problem can be prevented. On the exam, You may see questions where the best answer is to strengthen detection and monitoring rather than adding another barrier, especially when constraints prevent redesign. Remembering that controls have types and purposes helps you pick answers that match the scenario's needs. Assurance is a term that often sounds abstract, but it becomes concrete when you think of it as justified confidence. Assurance is the degree of confidence that a system meets its security requirements and will continue to do so under expected conditions. This matters because many organizations confuse having controls with having assurance, and the difference is evidence. A beginner mistake is to assume that if a control exists, it must be effective, but engineering requires you to verify and validate, and operations require you to monitor. Assurance also ties to accountability because decision-makers need a basis to accept risk, authorize operation, or approve changes. Exam questions may ask about what provides confidence, and the right answer often involves evidence, traceability, testing, monitoring, and discipline change control. If you recall assurance as confidence backed by evidence, you can see why it is central to security engineering rather than optional paperwork. Verification and validation are closely related and often confused, so having a plain language distinction is very valuable. Verification asks whether you built the system correctly according to requirements and design, while validation asks whether you built the right system that meets the real needs and operates safely and securely in context. This matters because a system can be verified and still fail in the real world if the requirements were wrong or incomplete. Beginners often treat testing as a single thing, but engineering uses different kinds of checks for different purposes, and that difference is part of assurance. On an exam, verification is commonly connected to traceability and checking that controls meet specified requirements, while validation is connected to operational reality, stakeholder needs, and whether the system behaves securely when used as intended. When a scenario describes a mismatch between documented requirements and actual outcomes, the correct reasoning often involves validation problems, not just verification gaps. Keeping these terms distinct helps you select answers that address root causes. Configuration and baseline are essential terms that connect security to change, and change is where many systems lose their security posture. Configuration is the set of settings and arrangements that determine how a system behaves, including what services run, what permissions exist, and how components connect. A baseline is a known, approved configuration state that serves as a reference point for comparison and control. These matter because without baselines, you cannot tell what changed, whether the change was authorized, or whether the system drifted into an insecure state. Beginners sometimes think security is about the initial build, but security engineering includes maintaining security through evolution, patches, and new requirements. Exam questions often test whether you understand that uncontrolled change breaks assurance, because evidence from last month does not guarantee security today if the system changed. If you remember baselines as the anchor that makes change measurable, you will better understand why configuration management is a security discipline, not just an administrative chore. As we finish, the point of an essential term glossary is not to turn you into someone who can recite definitions quickly, but to help you recall meaning fast enough to keep thinking clearly during scenario-based questions. When you understand terms like system, asset, threat, vulnerability, exposure, risk, requirement, architecture, trust boundary, control, assurance, verification, validation, and baseline in plain language, you gain a stable mental toolkit that travels across every domain. Each term becomes a lens you can use to interpret what a question is really testing, whether it is about structure, decision-making, evidence, or change. The mistake many learners make is treating vocabulary as separate from reasoning. But in security engineering, the vocabulary is the handle you grab to move a concept into action. If you keep tying each term to what it means, why it matters, and what goes wrong when it is misunderstood, recall becomes faster and more reliable. That is how you build security engineering fluency that supports exam performance without relying on brute force memorization.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.